Hello everyone. In this video we're trying to show that the bivariate normal distribution is a valid probability distribution. So in order to do this, we're going to have to do two things. One, we're going to show that the density function is real and positive. And just as with any continuous probability distribution, that the area under the density curve is 1. So I'm going to start by actually writing the form of the density function. Now, because we have bivariate, so meaning two variables, therefore f of xy is going to be 1 over 2 pi square root of 1 minus rho squared times e to negative, and in the exponent we're going to have a fraction x squared plus y squared negative 2 rho xy divided by 2 times 1 minus rho squared. And of course a rho here is the coefficient of correlation. Okay. So first, in order to establish number one, that the density function is real and positive. Well, if we look at what this expression is made of, in front this factor, that's a constant, right, independent of variables x and y. Pi 3.14 and change, rho squared positive, and because it's bounded between -1 and 1, the radicand would be positive. So the fraction in front, this fraction is positive, right? So we know that that is positive. Let me do this. So this is greater than 0. Now look at the exponent. The exponent in the form of e to a function, a g of xy. Okay. Now, because exponential function is a positive function, therefore this portion, the function, is also positive. So what we have is we have product of two positive expressions, a positive constant and positive. Therefore, we have established one. So fxy is going to be positive for all x and y. Okay, that was the easy part. Now next we need to show that the area under the density curve is 1. Okay, now in order to do that, let's begin with, so we're working on number 2 now. So I'm just going to recall what the marginal densities of x and y look like. And remember, these are standard normal. So f of x is going to be integral negative infinity to infinity of fxy dy, right? And fy is going to be negative infinity to infinity of fxy dx. Okay. Now, the function here is going to be 1 over, this is the actual form of the density function, e to negative x squared over 2, and for y it's going to be 1 over square root of 2 pi e to negative y squared, y squared over 2. Okay, so we have that. Now, before I actually move on, I'm going to do something, because I'm going to need this during this process. This exponent in the original density, the exponent that you see here in the fraction, I'm going to complete the square in y in this fraction. So let's kind of do a sidebar here where I'll do that. So we want to complete the square. Complete the square in variable y. So again, if you noted that the expression in the exponent was x squared plus y squared negative 2 rho xy. Okay, now completing the square process, I'm going to group the y's together. Okay. And then if you recall from algebra, completing the square method, what we need to do is we need to add half of the coefficient on y squared. So that would be 1/2 of negative 2 rho x. quantity squared. Hold on, let me move away from the side. So I need to do 1/2 of -2 rho x quantity squared. That's what we need to do. And this will make this rho squared x squared. Okay, so that is indeed what I'm going to add and subtract from the expression. So this is going to be x squared plus y squared -2 rho x y plus rho squared x squared, and then minus rho squared x squared. Okay, the first two terms I'm going to factor x squared, so that's just going to be 1 minus rho squared when I factor it. And the second expression is a perfect square trinomial. The binomial form of this is going to be y minus rho x quantity squared. Okay, so that's what the numerator of that fraction is going to look like. That's the numerator of this fraction. Okay, and of course we have the denominator also. Now let me go ahead and bring the denominator into this. So when we go to the integration, it's just going to be really simple. Now at this point, I'm going to split this into two fractions. Okay, one is going to be this one, and then the second one would be the other one. Okay, this will be the second one. So we're going to split it into two parts. The first part, therefore, is going to be just x squared over 2, right? The 1 minus rho squares cross out. And the second part is going to be y minus rho x quantity squared divided by 2 times 1 minus rho squared. So this is going to be the exponent again in our density function, in our joint distribution. That's what I'm going to use in the exponent. All right, now we're ready to actually prove that the area under the distribution is 1. Now, so let's write the area as the integral from -infinity to infinity. And of course, because this is bivariate, we no longer have area actually. In the case of single variable, we have area. In this case, we have the volume. The volume under the density curve is going to be the joint, and then we have dy dx. This is what we want to evaluate. And this is going to be -infinity to infinity, -infinity to infinity, and those are the limits of integration on x and y. Remember, x, y are real numbers. And then we have 1 over 2 pi. I'm just writing the density, the joint density at this point. E2. Now, in the exponent, remember, again, I keep bringing this up. This is what the exponent was, but I completed the square in x, and this is the exponent now. So I'm just going to use that in my exponent. Okay, I'm going to use negative x squared over 2 plus y minus rho x quantity squared over 2 times 1 minus rho squared. And then, of course, we have dy dx here. Perfect. Believe it or not, we're almost done. Hard to see that. Okay, next I'm going to write this as -infinity to infinity. Now, the 2 pi, I have some flexibility with that. I'm going to write it as product of 2 square root of 2 pi. Remember, root 2 pi, that's just 2 pi. So that's what I'm doing. I'm using one of my square root of 2 pi's here at this point, instead of just 2 pi. So that's 1 over square root of 2 pi. And then with the exponential function, this is in the form e to the m plus n. So I can write that as e to the m times e to the n. That's what I'm going to do next. I'm going to split the exponent and write it as product of 2 exponential functions. So that's e to negative x squared over 2, the first part, times. And then we have the integral from -infinity to infinity of 1 over square root of 2 pi, right? That's the second square root. And then of course we have the 1 minus rho squared in there also, times 1 minus rho squared. And because they're both positive, we can use the multiplication rule of radicals and join them together. And then e2 negative, because I'm running out of room here, I'm just going to put that here. And then we have dy dx. Okay. Now, next, let's actually write this as integral from negative infinity to infinity of 1 over square root of 2 pi e2 negative x squared over 2. Now, if you look at the density function, okay, this density function here, all of this is a density function for a normal distribution whose mean, just put that here, whose mean is rho x and whose variance is 1 minus rho squared. Okay, it's this part. Okay, and remember, this portion we moved it to front. Alright, so I'm gonna actually go ahead and maybe write it down here for you. The integral from negative infinity to infinity of 1 over square root of 2 pi 1 minus rho squared, and then e2 negative 1/2 y minus rho x quantity squared over 1 minus rho squared, and then this is dy, right? This is going to be the area under a normal distribution whose mean is rho x and variance 1 minus rho squared. So all of this is going to be 1 for that reason. So the integral is going to be 1. So that's times 1. And then of course we have the dx, differential of x on the outside. Okay, so the volume is going to be, now what's in front here is going to be the area under the standard normal distribution with mean 0 deviation 1, right? Right here, that's the area under standard normal 0, 1, and that is 1. So we have established the fact that indeed this is a valid probability distribution. And so that's all we wanted to do. We just want to show that that was indeed a valid distribution. And maybe up here, because I have area, this is a case of two-dimensional one single variate, but because we have two variables, maybe we need to show that in this case the volume under the density curve has to be 1 in the case of bivariate. What I had was the general case of univariate or single variable. Okay, and with that we're done with this video.